Okay. Anybody have any questions from last time before I keep rolling? So last time I introduced the stress tensor, which is the main quantity that we're going to be dealing with in this class. Anyone remember what the units were for stress? Yep. So the units are force over area. So you can think of it as like a distributed load over an area, the same as pressure. Pascals are the SI unit. And so the way that worked is, so if you have a stress element, like this, where this is 5 megapascals. I'm missing one. You couldn't have equilibrium without this equaling this. That has to do with this stress tensor being a symmetric matrix. So let's say all this talk about stress gave you the hiccups. I'll do something scary pretty soon. That'll help. And then let's say this one is 10 MPa. Okay. So in this case, the stress tensor, if you have a coordinate system like this, on the positive x face, we have an x component in the negative x direction, so negative 10. I'm going to just list these all in megapascals, or in pascals, times 10 to the 6th. We have, in the y direction, we have a downward stress of 5 megapascals. We know it has to be 5 because of the symmetry of this matrix. This one is 5. So negative 5 times 10 to the 6th. And then nothing in the z direction. On the y face, symmetry says that this has to be negative 5 times 10 to the 6th. There's no normal stress. And then in the z direction, there is a negative stress of 2 times 10 to the 6th. And then on the z face, we have nothing in the x direction, which this one has to match this one for symmetry. Negative 2 times 10 to the 6th in the y direction, and nothing in the normal direction. The diagonals are called normal stresses because those are the components of the if you think of these as distributed load vectors on each face, the diagonal ones give the components that are perpendicular to the face. And the off diagonals, the ones that aren't diagonal, are called the shear stresses. Yeah.
Where it's kind of a known that the vector without like 2 by it.
Mm-hmm. Well, yeah, if you, so the way it works is, okay, so, so it doesn't rotate. That's exactly right. It's, I might as well say that. So why does sigma, in this case, xy equals sigma yx, and sigma, what's this one, yz equals sigma zy, and, well, this one doesn't appear in this problem, but symmetry says that sigma xz has to be equal to sigma zx. That's all related to rotational equilibrium. So it's due to moment equilibrium. So if you think of a block like this, if you have a force going this way, let's see. You have to have a force going this way, a force going this way, and a force going this way. So these forces, they're not really forces, but forces per area, must be equal to satisfy both sum of the forces equals 0 and sum of the moments about the center equals 0. Okay, you can try to come up with a way to make it work without that, and you'll see that it's not possible. So that's why these have to be equal, and therefore that's why this matrix is symmetrical. It has to do with equilibrium according to Newton's laws. Any other questions? And we can also write it in the Voigt form. So the Voigt stress. Oh, I haven't defined that yet. Hold on. I haven't talked about that at all. Okay, I'll do that later. Okay, so here is a really cool thing, very useful thing about the stress tensor. And this has to do with the relationship between the stress tensor and tractions. So I have to tell you what a traction is. Tractions are vectors. So the traction vector is the distributed load vector let's see, acting on any face of a chosen object. Chosen body. The units for traction, since we're talking about a distributed load acting over an area, is going to be the same as it is for stress. So it's going to be force per area. And the SI units are going to be pascals. And if you take the stress tensor and multiply it by an outward facing unit vector, so this is an outward normal unit vector to the face, it gives you the traction vector on that face. So that's not time. In this class, actually, we're never going to talk about time. In this case, that's a traction vector. Well, it's per area. You like a lowercase f? Yeah. That would make more sense. I don't know. They probably didn't think it through very well. Traction vector. Yeah, lowercase f seems like a good idea, but they didn't. Okay, so first let's see. I mean, we'll see how it works. So here's our first thought. Check out this equation on a stress tensor, or a stress element. Okay, so for example, let's say that this is the stress element. Let's say we have 10 megapascals acting in the positive z direction on the positive z face. 1 megapascal acting down on the z face. 2 megapascals acting to the right, and then make all these corresponding shears that would make this a symmetric matrix. And I guess let's put one more here. And say that we're going to use this equation to calculate the traction vectors on each of the 6 faces. Well, let's not do all 6. That'd get a little tedious, but let's do 3 of them. So let's do 2 positive faces and 1 negative face. So I don't know, let's do plus x, plus z, and minus y faces. Okay, so on the plus x face, that's this one. what's that traction going to be? What's the x component of the, so on this one here, the positive x face. So it's going to be positive 7, 0 y, and then positive 2, right? The stress tensor is 7, 0, two, then 0, 0, yz is -1, and then 2, -1, 10. Okay? Does that look right? Okay, and now if we're trying to calculate the traction on the positive x face, what's an outward facing unit vector to the normal to the positive x face? What? Well, I'm just trying to come up, just tell me what this unit vector n is that I have to multiply to calculate this traction. Well, the x face, it's going to be 1, 0, 0. It's just going to be, so 1, 0, 0. And so we get 7 times 10 to the 6, 0, and 2 times 10 to the 6. Any questions about that?
That's the unit vector of the x face.
Yes, and it has to be the unit vector coming out of the face from the middle of the body. Okay. This should have they should all be times 10 to the 6. Okay. That's just for the positive x. Okay, now let's do it for the positive z. Same stress tensor. What's a outward normal for the z positive z face? Yep, 0, 0, 1. And so you get 2 times 10 to the 6, -1 times 10 to the 6, positive 10 times 10 to the 6. Okay, and then for the last one, we want to calculate the traction on this face that's underneath, the negative y face. So we have the same, we start with that same stress tensor. And what's an outward pointing normal for the negative y face?
0, -1, 0.
Yep. 0, -1, 0.
Even if there is no normal stress on the y face?
That's right. You know, that traction, I mean, if there's no normal y stress, then that traction is going to tell us that. You know, the traction vector can come out to be 0, or it can come out to only have. So what we're going to see here is that, well, let's do the calculation and we'll see what it shows. So you get 0 because it's pointing out of the negative y face. And then positive 1 times 10 to the 6 pascals. So this shows the traction vector on the positive y face. For equilibrium, we need to have the opposite traction vector on the negative y face. And this says that there's, you know, it says what we see in that picture of the stress element. There's no component on the y face, there's no component of the traction in the y direction. There's also none in the x direction, but there's one in the z direction. Okay, so is this like the most pointless factoid ever, or who wants to guess? No, there's a lot of factoids. I mean, it would, you know, like, this would have to be pretty bad to be the most worthless one ever. But I'll even go beyond that. And this ends up being really useful, really important. Okay. This seemingly useless fact turns out to be very helpful. I'm good. That's only the start. That's the first line of the proof. Okay, so let's say that we have example 1. Say that we have a material like this. So this is all solid. Okay, goes off into the distance. And let's say that this makes an angle of 45 degrees. And say that we have a way to measure the stress of material points along this edge. And we get that we get, 2, 0, 1, 0, negative 5, 0, 1, 0, 8 in megapascals. And the question that we can answer is, what's the distributed load along the edge? Well, we take the stress tensor, multiply it by an outward-facing normal to that edge. So who can come up with the outward-facing normal to that if this is our coordinate system? So that would be, so you can start here. so, I mean, it's just going to be 45 degrees. You can think of starting here, going 135 to get here, and then going 90 back this way to get here. So positive 135 minus 90 gives you plus 45. And so you have cosine and sine of 45. And so this is 0.7071, 0.7071, 0. And so the traction, the distributed load acting along that face is 1.414 megapascals what's 5 times? Oh, be quiet. Negative 3.535, I think. And then 0.7071. It's amazing. Every dog has his day. Yeah. Okay, so that's one application of this. What's a more likely use for this, because it tends to be easier to measure external loads than to measure stresses, is to be given a traction on a face and use that to come up with limitations on the stress of the points at that face. So let's say that, say we have a block of okay, so say we have this big chunk of material. And there's a total, like distributed uniformly, there's a total force of 25,000 newtons acting. And let's say that this is 10 centimeters, 0.1 meters, and this is 0.1 meters. What do we know about the stress tensor? You know, the stress tensors for the points at the end. Okay, well, the first thing we have to do is represent that, you know, translate that force of 25,000 newtons into a traction. So yeah, that's so I guess that's just going to be so 25,000 times 100 is 2.5 megapascals, I think. Calculator boy, check my work. Okay. Yeah, exactly. Okay, so the traction vector is, and what direction is it in? It's a vector, right? So it's negative 2.5 MPa 0, 0. Okay. The stress tensor, so we're going to start out by saying we don't know anything about it. times the outward facing normal. What's the outward facing normal for that face? 1, 0, 0. And we know that that has to equal negative 2.5 times 10 to the 6, 0, 0. So that gives us three equations that say sigma xx is equal to negative 2.5 times 10 to the 6. Sigma xy is equal to 0. And sigma xz is equal to wait, what? Yeah, right. Sigma xz is equal to 0. Okay, so it doesn't tell us everything about the stress tensor. But whereas before we had 6 unknown values, now we know that we have 2.5 times 10 to the 6 there, 0 there, 0 there, 0, 0, and then these are still unknown. This approach is really useful for coming up with boundary conditions, and in any kind of mechanics problem, boundary conditions are, finding the boundary conditions is a lot of times the main challenge in doing the problem. One other important application of this idea for this relationship between stress and traction is we're going to use this in our derivation of the principal stresses. So a lot of times, used in deriving principal stresses, and we'll talk about that in not too many more class periods. So one of the things you want to do when you calculate stresses is you wouldn't really care that much about you don't tend to care that much about how much of the stress is directed in the x direction on the x face and how much is directed in the y direction on the z face and stuff. What you really want to know is you'd just like to know in a general overall sense how big this stress is, how likely the material is to break. And principal stresses are really important for doing that because they give you a way to find the maximum normal stress and the maximum shear stress. So principal stresses are going to be a really important thing for determining how likely a material is to fracture. And in deriving the principal stresses, we're going to use this idea of tractions. Okay? Any questions about that? All right. I guess this is a pretty good place to stop. Next time we're going to talk about strains. So stresses are essentially a point-by-point measure of the loading, the internal loading at that point. Do you remember what I said, just like in passing? What are strains? A point-by-point measure of deformation. Yep, exactly. And so that's what we're going to get into next time.